Hey guys, my name is IBM and I'm solving the last part of this paper. This is going to be part 5, which is questions 9 and 10. Like I said, I decided to make the videos to be shorter and give more explanations or clear explanations because students they always want to take a break when they are learning or they are revisiting concepts. So question 9, polonium 193 is an unstable nuclide. A nucleus of polonium-193 decays to a nucleus of lead-189 by emitting an alpha particle. You and me know that alpha particle is alpha 42. Radioactive decay is both random and spontaneous. State what is meant by random. Of course, random means we cannot predict which nucleus in a given sample is going to decay next. And spontaneous means nothing in the environment affects or influences the decay. So random means can not predict which nucleus in a given sample will decay next. So you can't single out any nucleus in a given sample which is going to decay next, but you are sure that at least a nucleus is going to decay. Spontaneous means nothing in the environment can influence or affect the decay, so not affected by external factors such as temperature, pressure, catalysts, etc. So nothing in the environment affects, or nothing in the environment influences the decay. Define half-life. Of course, the time taken for the activity of a given sample to reduce to half of its original value is the half-life, or the time taken for the number of undecayed nuclei in a given sample to reduce to half of its original value is what we call half-life. So time for the activity of a sample to reduce to half of its original value is what we call half-life, or you can say it is the time for the number of undecayed nuclei to reduce to half of the original value, or half of the original number. So that is half-life. Of course, activity is the number of nuclei decaying per unit time, or the rate of disintegration. The data for the binding energy per nucleon of the particles involved in the decay of a nucleus of polonium are given in the table. So they've given us the particles, polonium, lead, alpha, and they've given us the binding energy per nucleon. So polonium, which is PO 193, 84 is decaying into lead, which lead is 189, and this is 82 plus an alpha particle, which is 42. Determine the energy in electron volts released when a nucleus of polonium decays into a nucleus of lead. So we are looking for just change in energy. So of course, this is binding energy per nucleon. So to find the energy, it's going to be binding energy per nucleon multiplied by the nucleon number to find the energy. So we want the difference in energy is going to be the energy which is released. So this is on the left hand side. I think on the right hand side, total energy is greater. We just want a difference in energy. So this is going to be 7.074 for alpha times the nucleon number, which is 4. Then plus on the left again, we have lead, which is going to be 7.826 times the nucleon number, which is 189. That is total energy on the right hand side. Then minus energy on the left hand side, which is going to be 7.774 times the nucleon number, which is 193. So I'm multiplying binding energy per nucleon times the nucleon numbers to find the difference in the energy, which is going to be the energy released. If the energy is released, it means that energy on the left of the products is smaller. So pressing my calculator, I will have that 7.074 times 4 plus 7.826 times 189 minus 7.774 times 193. So this is giving us, did I press the calculator correctly? This is really big. Let me check again. 7.074 times 4 plus 7 point, sorry, I have to open this bracket again. 7.826 times 189 minus 7.774 times 193. That is 7.028 joules. So the energy released is approximately 7.03. Sorry, this was electron volts, not joules. Then part D, a pure sample of polonium-192 contains N0 nuclei. After time t, the sample contains N nuclei of polonium. The variation of ln of N over N0 with the t is shown in the figure here. We know that N equals to N0 e power negative lambda times t for decay. So that means that N over N0 equals to e power negative lambda t. When introduce natural log, ln of N over N0 equals to negative lambda times t. When you compare this with y equals to mx plus c, there is no, so this one means that if I have this on the y-axis and I have, is it time on the x-axis, time is on the x-axis, so it means that the gradient is going to be negative of the decay constant. So state the name of the quantity that is represented by the magnitude. Since it is magnitude, I will not mention the negative magnitude of the gradient, so it represents decay constant. Use figure 9.1 to determine the half-life in milliseconds of polonium and negative polonium-193. So we have said that negative decay constant is the gradient, or gradient is negative decay constant. So this is going to be equal to, I'm just going to take, let me just take this, and the starting point is 0, 0, so that one gives me a gradient very easily. So this is going to be negative 1.0 minus 0 divided by the corresponding value of t. T is equal to 0.6. You can choose any other pair of values. So this is 0.6 minus 0. This gives us a negative 1 over 0.6. So that means the decay constant is equal to 1 over 0.6. And you also know that the decay constant equals to ln of 2. Remember, this was in milliseconds. This one has no units. This one is in milliseconds. So this is in milliseconds. So the decay constant is ln of 2 over t half, or over half-life, which means that the half-life is going to be ln of 2 divided by the decay constant. That is ln of 2 divided by 1 divided by 0.6, which is the same as 0.6 milliseconds times ln of 2. So 0.6 times ln of 2, that is 0.416. Or I can write 0.42. Positron emission tomography, that is PET scanning, uses a radioactive tracer. Okay, that is also in medical physics. State what happens to the positrons emitted by the tracer. Of course, during the PET scan, you are injected with what we call a tracer. And the purpose of the tracer is to produce the positrons. The positrons are supposed to interact with the so many electrons we have in the body. Remember, the electrons are the antiparticles of the positrons, so their energy, total mass, is converted into energy in the form of gamma ray photons. So the positrons interact with the electrons, or collide with the electrons. So the positrons interact, or I will say collide, with electrons in the body, so that their mass is converted into energy of gamma photons. Explain why a tracer with a half-life of approximately 2 hours is a suitable tracer to use. So 2 hours appears as if it is long enough for the to conduct the scan, or to conduct the investigation, but also it is a shorter time for the tracer to stay longer inside the body. So that means 2 hours is favorable. So 2 hours is long enough to have time to conduct the investigation, but not so long. But not so long as to cause the patient unnecessary exposure to radiation. to cause the patient unnecessary, what's the spelling of necessary? Unnecessary exposure to radiation. So in 2 hours, the scan can be complete. So that means the time is long enough for the scan to take place. But also 2 hours is not so long for the radiations to remain in the body for a long period of time. So the patient will not be exposed to radiations for too long, because 2 hours is not so long for the radiations to cause damage to the patient. Okay, and lastly, this is question 10, and it's the last question. State what is meant by luminosity. So this is astrophysics and cosmology. I think my students find this as the easiest topic, but sometimes it becomes technical. Some few questions can be technical. So what is meant by luminosity? Whenever you're defining luminosity, refer to the total radiant power. Radiant power emitted by a star. Total radiant power emitted by the star, that is the luminosity. Explain why standard candles are used to determine the distance to a galaxy. Of course, a standard candle is an object of known luminosity, and that means if the luminosity L is known, what we remain with is to measure the radiant flux intensity which is observed on the Earth's surface. And therefore, using the equation which is F equals to L over 4 pi d squared, we can use the standard candle to determine the distance of a galaxy from the observer. So I would say a standard candle has a known luminosity, call it L. A standard candle has a known luminosity, call it L. So by measuring the radiant flux intensity, F received, radiant flux intensity F received by the observer the distance to a galaxy can be calculated from F equals to L over 4 pi d squared. So the distance can be calculated from F equals to L over 4 pi d squared. The sun rotates on its axis. Points X, Y, and Z are on the equator of the sun as shown in the figure. So they are on the equator along the imaginary line drawn just above the Earth's surface on the equator. The wavelength of light from points X and Y are observed and recorded. So this is the equator of the sun, not the equator of the Earth. So observed wavelength from X. The observed wavelength from X is this one, and the observed wavelength from Y is this one. So notice that the observed wavelength from X is greater than the observed wavelength from Y. and yet all the 3 points are on the equator of the sun. Okay. The sun rotates with a period of 2.07 times 10 to the power of 6 seconds. Show that the radius of the sun is 6.93 times 10 to the power of 8 meters. So they have given us the period. We know that V equals to omega times R, and omega is 2 pi divided by period, then this times R. And also we know to find the speed V, we know that the ratio of the frequencies, the apparent frequencies, is the same as the ratio of the wavelength, is the same as V over C. This is also given as the Doppler equation. So I'll just use the one of wavelength. So it means that if V equals to the change in wavelength, or the difference in wavelength, which is 656 point, I think it was 2877, then minus 656.2831 divided by 656.2831. Of course, we divide by, because y is at the center of the axis of rotation, then y is going to be the reference point. So that is going to be 656.2831. Then this is going to be multiplied by 3 times 10 to the power of 8. I'm making V the subject from here. So this means that V equals to 656.2877 minus, okay, then times 3 exponent 8. Divide this by 656.2831. So this is giving us 2103. So we are finding the radius of the sun. So the radius of the sun is going to be V times the period divided by 2 pi. So that is 2103 times 2.07 times 10 to the power of 6 divided by 2 pi. I'll just multiply that by 2.07 exponent 6 divided by 2 pi. So I'm getting 6.927 times 10 to the power of 8 meters, which is approximately 6.93 times 10 to the power of 8 meters. Remember, the examiner wants to see the answer which rounds off to what has been given. State and explain how the expected wavelength of the light observed from Z compares with the emitted wavelength. So the expected wavelength of the light observed from Z. Now note that it is moving. The sun is moving in the clockwise direction according to this arrow. It is moving in the clockwise direction. So the wavelength at X was greater than that observed from Y. The wavelength observed from Y is this, and wavelength observed from X is this. So if this rotation is clockwise, it means that Y is going to be moving towards the Earth. Y is going to be moving towards the Earth because its wavelength is smaller, but we want the wavelength of light observed from Z in comparison to what is emitted. Because now the sun is moving, rotating clockwise, it means Y is moving towards the Earth, which also means the point Z if I had a 3 dimensions here, I would show the sun rotating about its axis. So y is moving towards the earth, since the observed wavelength from y is less than that from x. So it means the observed wavelength, which is coming from z, is also going to be less than um, the emitted wavelength, because the rotation is actually clockwise. So y was moving towards the earth because the observed wavelength was less. It means because the rotation is clockwise, it means z will also be moving towards the earth, which means that the observed wavelength from z is going to be less than the emitted wavelength. That is in accordance to the redshift. So y is moving towards y is moving towards y is moving towards the earth, since the observed wavelength from y is less. The observed wavelength from y is less. The observed wavelength from y is less, so it means y is moving towards the earth. And since the rotation is clockwise, it means z will also be moving towards the earth. That means the observed wavelength from z is also going to be less. So observed wavelength from z is also less than the emitted wavelength, since it's also moving towards the earth. Okay, then the luminosity of the sun is 3.8 times 10 to the power of 24 watts. Use the information in B Roman 1 to calculate the surface temperature of the sun. Of course, the equation relating luminosity and temperature is given in the list of formula, that luminosity L equals to 4 pi times R times sigma squared luminosity is given as 4 pi sigma r squared t to the power 4. It's given the list of formula. So making t to the power 4 the subject. So this is going to be the luminosity, which is 3.8 times 10 to the power of 26 watts divided by 4 pi. Sigma is given the list of constants, which is 5.67 times 10 to the power of minus 8. Then times the radius. We have said the radius was 6.93 exponent 8. So this is 6.93 times 10 to the power of 8, but this should be squared. Okay, so I will just press my calculator. So I have 3 exponent. Now let me start with the denominator. 4 pi times 5.67 exponent minus 8. That is Stefan Boltzmann's constant. It's not Boltzmann's constant, but Stefan Boltzmann's constant. Then times, open brackets, 6.93 exponent 8, but this is squared. Then I'll get 3.8 exponent 26 and I divide by the answer. So t to the power of 4 is equal to that. T to the power of 4 is equal to that. 1.1105 times 10 to the power of 15. Then I get the fourth root. So I will raise this to the power of 1 over 4. So I can find the root. Now I'm going to find the shift root of the answer. I'm going to just change the root to the fourth root. The fourth root of the answer, and it is 5772. So T is equal to 5772 Kelvin, 5773 Kelvin, which is approximately 5800 Kelvin. Okay, so that was the paper. I took a lot of time because I tried to be very careful with explanations, but at least I've tried my level best. If I was answering it normal, I would use less time. But since I wanted to give simpler explanations, I think I've tried my level best. Until next time, bye bye.